Tonight we're here to listen to Patrick, do you pronounce it Hebron? Hebron?
Hebron.
Hebron, there we go. Talk about machine learning and its future, especially as it relates to designers' work. As a software developer, designer, teacher, author, and the lead of the machine intelligence design team at Adobe, Patrick's work with machine learning includes both understanding the ways we will work with machine intelligence in the future and also how to share that understanding with non-developers, especially designers and other creatives. He has worked on and written about, among many things, machine learning-based design tools, philosophies of machine learning and the human mind, and the merits of certain films. I, for one, am looking forward to hearing about how we as designers can prepare for the likely ubiquity of machine learning. Please join me in welcoming Patrick.
Thanks everybody for having me. I was just talking with Marco about, I think, when we founded the team about a year and a half ago, it's like hiring sort of poses a unique thing because it's sort of a new field, and you always think kind of like, well, what did people get a degree in the first generation of a field, right? Like, what did the first generation of computer scientists get a degree in? Obviously, it wasn't computer science. There was, probably applied math or something. But, in sort of the intersection of machine learning and design, I think just now we're starting to see sort of, the programs like this start to look at this kind of subject. I went to NYU ITP, and, I think in some similar ways also looking at that there. So anyway, it's great to be here, and let's get started. OK, so maybe I'll just kind of give you an overview of the structure of the talk. I was going to just talk a little bit first about what machine learning is. I'm going to frame this in terms of the ideas of induction and deduction, look at some puzzles almost, and then start to talk about kind of the design implications, some of the opportunities through design, as well as some of the challenges that are unique to machine learning. And then in the final section, hopefully we'll have time. If not, we can turn it over to Q&A. In the final section, talk a little bit about some of the stuff we're doing at Adobe. I'd love to show you all of the stuff we're doing, but some of it will have to wait. OK, so what is machine learning? All right, so I think the way that I think about this is the difference between deductive and inductive reasoning, which are kind of the two main forms of reasoning in general. And so deductive reasoning is when you go from the general to the specific. So you start with some kind of broad theory about what's going on with a particular system. To make this more palpable, maybe you observe some behaviors in the world, like something related to physics or something, right? And you kind of have a theory about why objects fall when you let go of them or something like that. And this kind of general theory leads to more specific hypotheses, and then you try to observe the world as much as possible in varied conditions and so forth, and ultimately try to take those observations and try to confirm the hypothesis in the theory. Inductive reasoning is essentially the reverse of that. So you start from no general theory, and instead from very specific observations, and you try to see patterns across those specific observations, those particular examples. And from that, try to build up hypotheses and ultimately to some kind of generalized theory. OK, so one way to think about this is that you could say that an equation is the general, right? And a specific is when you plug specific values into that equation, right? So doing this with physics or something would be a more complex equation, but for something like a straight line equation, we're going to have some particular formula, and then we can plug any particular point into that, right? And so if we have the formula and we want to sort of plot it out, we just would sort of give a bunch of x's and get out the y's, and then we'd have our line. We could also go in the opposite direction, right, and try to look at, if we were just given these specific points, could we sort of try to figure out what the equation for the line is? So going in the deductive direction works for a lot of things quite nicely. But there's certain things where it's kind of hard to to figure out how to write a general equation, right? So like if you tried to write a formula to describe all possible facial appearances, it'd be intractable really, right? Like, people look many different ways, and then each of those people could be seen in a wide variety of lighting conditions, and from a wide variety of camera angles. And so, if you were trying to sort of, make this as like a series of if clauses, it would be essentially impossible, right? You'd sort of, keep trying to add clauses to make this closer and closer, and then you'd find that it didn't work with one particular person or one particular lighting condition. You'd try to add some more clauses, and you'd never, ever get there. And so these kinds of problems are ones that perhaps make sense to go in the opposite direction, right? It's very hard to describe the general formula for faces, but we've got a really good number of examples of what people look like, and so perhaps we can kind of figure out how to approximate the general formula for the appearance of a face by looking at many examples. Okay, so in one sense or another, people do this, of course. But how does a machine approach this? Okay, so here's a very simple puzzle rule system, right? All of the green figures are included by some rule. All of the red ones are excluded by that rule. Okay, so we look at these, and then we ask the question of which of these shapes in black are included by the rule and which are excluded. And perhaps more importantly, then what is that general rule? So this one I'm sure you figured out quite quickly, right? The general rule here is that the rule of inclusion is that the shapes are open and closed shapes are excluded. And so now you can apply that to all of the other examples. Right, and think about kind of even though it's a very simple problem, think about sort of the mental process that you go through in figuring this out, right? In a sense, with one this easy, you might just kind of almost feel like it's immediate, right? It just sort of comes to mind. So as we look at a slightly harder one, think about kind of your thought process as you try to figure out what the rule is here. Okay, so the rule here is actually a little bit misleading. It's that all of them are this particular height. Okay, and the reason I do this is because like what you have here is noise, right? Like you have some other properties involved. You have closed and open shapes. You have shaded and non-shaded shapes, right? And as you're trying to think this through, you're looking at all of these, and you're sort of trying to work through the rule. And perhaps the way that you're approaching this is to kind of choose a particular hypothesis and say like, oh, maybe it's whether it's open. But then, of course, you sort of look at the examples and you say, well, no, that can't be because here's a closed shape and here's an open shape that are both included, so it can't be that. Or maybe it's shading. No, it can't be that, right? And you sort of work through this and sort of check against the examples and ultimately try to kind of generalize from that. And of course, one of the main reasons why this one is more difficult than the previous is because of the noise, right? Like there are multiple variables involved, and it of course seems that they may be of significance, but it turns out that actually only one was of any significance. And this, of course, is very true of the real world too, right? So, in addition to what we were saying about faces of like there being a wide variety of how people look in different lighting conditions and different camera angles, there can also be just like noise and grain in an image, right? And so when you're trying to decipher the pattern of a face, you also have to decipher objects that are occluding it and noise and any number of factors that sort of contaminate the concept that you're trying to distill. But with enough examples, you can start to get at it. All right, so I'm sure you've got the point. I won't belabor that one. All right, so now let's kind of think about how this is something that you could implement in a machine. So this is sort of a truth table for one particular rule, right? And we'll say that shaded and closed figures are included, and all of these other permutations are not included. So in other words, like in sort of formal logic, this would be an end rule, right? If it's closed and shaded, then true. Okay, so think about this as like a circuit of sorts. Obviously, like the sort of comparison to neurons maybe also makes sense, but usually better to stay away from that. So with a sort of a simple electrical system, how could you implement this? Okay, so first of all, let's just assume we have these two inputs, right? And they're, basically there's either voltage going through it or there isn't. Sort of like on-off, right? And then the given here will be that we have a decision node, right? Like essentially a transistor. And if the sum of the input signals is greater than or equal to 1 volt, okay, then the voltage is going to go through and like a light will go out on the output, right? Signifying true. Okay, so assuming that we need 1 volt to do it, what voltage should we assign to each of these? Well, if we assign, say, 1 volt to each of them, right, then either of them independently would trigger the output, right? If this one was on and this one was off, you'd have 1 volt and the output would go on, or vice versa. So that would be equivalent to an OR rule, right? If instead we had a ½ volt for each, then only that, would you have the sum of them equal to 1, and this would kind of, trigger the output. So, sorry, just looking ahead. Okay, so, this is something you can kind of figure out like in a fairly procedural way. But another way of approaching it, right, is to try to induce this. And so, the way that you could think about that is, well, pick random numbers for each of these two voltages, right, and then try them out and see whether the results match, the expected behavior. And if they don't, then kind of start to adjust each of those two voltages until you sort of find something suitable. So this actually is, in a sense, kind of the sort of core element of how a learning system works, which is that you start from kind of a random perception of the world. You don't really know what should be true. And you try values, and you pass them through, and you check them against answers that you know to be correct or incorrect. And when you're incorrect, you start to adjust the values and ultimately sort of come to levels that are better. Okay, so this little sort of formulation here is equivalent to something called a perceptron, and it was one of the first neural networks that was developed. It turns out that there are certain types of problems that can't be solved at all with this. And basically, well, I'll get into why in a second. Okay, so here's kind of the problem of what's wrong with that. Generally speaking, in the real world, you're going to have like observable causes and observable effects, right? So, well, I guess that's all that there is to say about it. You have causes and effects, right? But underneath that, there are some set of things that are influencing these behaviors that you can't, sort of fully observe, right? So, like, if you drop a ball and it falls, you could say that you have sort of the cause and effect there. But of course, the part that is not directly observable is the behavior of gravity. And so you have to assume that there are underlying factors that ultimately are kind of guiding what's going on here. And you kind of can't directly see them, but you can kind of understand them as being sort of a correlation that explains the relationship between the inputs and the outputs. So the big innovation that happened in machine learning is something called backpropagation. And basically this sort of one procedure is sort of the thing that fuels all of contemporary machine learning. And essentially what it is it sort of figures out how to kind of implicitly understand what these things are without knowing what they are directly. So if anyone's taking calculus, really what the backpropagation is it's an application of the chain rule. And so in other words, what you do is you sort of say like, we're going to adjust all of these values in relation to one another, but we don't really know what these sort of middle things are supposed to represent. However, if we sort of start from, we pass information from the input towards the output, and we look at examples where we know what the answer should be, then this thing is essentially, by passing information in this direction, you're sort of taking a guess, effectively. That guess is likely to be very wrong. And so then you look at how wrong you were, and you treat every layer backwards as sort of a nested function of the previous. And through this, you sort of are somehow able to essentially kind of infer what those unobserved behaviors are. as nested functions of your incorrectness. It's sort of weird that this works actually. That you can sort of figure out like what is sort of the underlying factor without being able to observe it, but nonetheless it does work. Okay, so kind of a goofy graphic for this, but with things like human behavior, right? Like you see people acting on the world, but of course there's many factors in their behavior that are not available to you, right? Like you don't sort of know necessarily what motivates them. So for example, when a person picks a car, right? The car has certain properties, and some particular customer might have some particular opinion of this or rating of it, right? And presumably, there's a relationship between the properties of the car and how this person perceives the car. So, this person happens not to be a big fan of sports cars. They're a much bigger fan of family sedans. So perhaps we can start to surmise that some of these underlying causes might have to do with their interest in safety over speed. And of course, if we kind of toggle between these, if we only have like one example here, it's very hard to sort of remove the ambiguity of what properties are of significance. Particularly, right, if we sort of look at just these two. We have maybe some sense, but we can't, for instance, tell whether speed or style are of greatest significance. But when we introduce more examples, then we can start to disambiguate this, right? So if we see here, the rating stayed the same, but the style level went up, right? And so therefore, we can infer that style is not particularly of significance to this person, right? And so with each additional example, we're able to kind of better generalize the overall rules of the system. Okay. So now I want to talk about how machine learning is a bit different from conventional code. All right. So the first difference is that it kind of operates in a different domain of logic. So conventional code operates on formal logic, Boolean logic, right, in which everything is ultimately reducible to an either true or false statement. The way we operate in the world is often referred to as fuzzy logic and really does not usually reduce to something that's true or false, right? So when we speak, we refer to things as being very small or slightly green or pretty nearby, right? And these are not exact ideas. They're, well, fuzzy ones. And of course, any one of these descriptors is very much context dependent, right? So when you refer to small in the context of a car, you have one kind of meaning. And when you refer to small in the context of a planet, you have a very different scale in mind. If you'd only seen one car ever, you would really not be able to say whether this is a small car or a large car, right? And if you'd seen two cars, now maybe you have a little better sense, right? But still, perhaps you don't have a very good sense of kind of the full range of what car sizes are. With each additional experience, you're starting to get sort of a better and better mapping. And really, no matter how many cars you've seen, you can never truly have a formal guarantee that you actually know kind of the full range, right? It could be that somewhere in the world there's a car that's smaller than any you've ever seen before, and that kind of can never change. But with a sufficient number, you ultimately can sort of get to the point where you can have, if not a guarantee, at least sort of a strong sense that your sort of experiential range is going to match more or less to the ranges experienced by other people, right? And once you have that, then you can begin to communicate with other people in a way that's going to be meaningful, so that when you say small car, someone else is probably going to picture a similar type of car to you. Of course, computers don't live in this world, right? They don't, have sort of immediate access to the experiential ranges. They, well, jokingly live in darkened basements or data centers or whatever. And so, therefore, conventional machines are not really able to operate in the domain of fuzzy logic. We can't, say to our ATM that we want to take a little money out of it, because a little money means different things to different people, right? And they have no access to that. So machine learning is, of course, about learning from experience and learning from data. And this is how we can sort of begin to change the story of how we can communicate with machines, is by exposing them to experiences that are hopefully indicative of the range of things that exist in the world. OK, so machine learning also suggests a very different kind of software development process. Conventional software, you can see, is being really like a very elaborate form of choose your own adventure, right? If you want X to happen, then you go to this part of the code, and if you want Y to happen, you go to this other part of the code. Something like this. Of course, conventional software can have bugs. There's no shortage of them. In this case, we haven't covered the clause of, we've covered the clause for if the grade is greater than 65 and if it's less than 65, but we haven't covered what happens if the grade is equal to 65. Even though this is, always going to be there and always something you sort of have to, chase after, there's at least a way that you can approach the problem, right? You can sort of systematically look at this and try to sort of basically walk every possible branch of the tree and look at whether everything's covered, right? And this is debugging. This is much less true for machine learning, because machine learning systems are inducing their understanding of the world from many examples. And so as per sort of our own experiential understanding of things, let's say that a machine learning system has been exposed to many images of cars, but not of one particular type of car. Well, if you thought of that ahead of time, then great, you would then train on that type of car. But sort of what you don't know that you don't know is of course, sort of the greatest enemy. And so, there's kind of no suggestion in the system that it's not aware of, any examples of red cars or something, right? And so it's only when, say, a user tries to pass a picture of a red car through your system and gets bad results that you then learn, like, oh, this thing was not able to handle that, right? But the sort of the representation, in kind of the mind of the machine doesn't make that obvious in any way. So to make that point sort of a little more tangible, this is a neural network I built. And this is basically sort of a visualization of all of the neurons in the machine. Despite having built this system, there's no way that I could tell you, whether it will perform well on some particular task, right? What is covered, what is not. Ultimately, these are sort of these loose connections, as per those earlier diagrams, where you have kind of what's called a distributed representation, right? You're sort of looking at these kinds of correlations between your observable inputs, the underlying factors, and the observable outputs. And all of that is essentially represented here, but in this kind of very abstracted form. So this does not lend itself to debugging in the conventional sense. We'll talk more a little bit later about sort of some strategies for how to sort of approach something in the vicinity, I guess you could say, of debugging. OK, and so I'll point out that as much as we have very sophisticated neural nets in our own heads, and as much as we've had a great deal of experience, we still sometimes make the kind of perceptual errors that we would also see from learning systems. So I'm always unsure whether this image appears well from different angles, but this is a grilled cheese sandwich that caused quite an uproar some years ago when people noticed that it looked like an image of a woman, or I think specifically Mother Mary, in the grilled cheese sandwich. And like, I think the sandwich actually sold on eBay for like a great deal of money. But anyway, like, we see this too, right? A face in a cloud or in the grain of wood or a grilled cheese sandwich. And so these kind of perceptual errors are sort of inherent to the nature of this kind of learning system. They can do very powerful stuff, but at the same time, it's really kind of impossible to guarantee that they will always be correct. And so that takes us to this different kind of precision. So conventional programs are always correct about mundane things. And by mundane, I mean that in a specific way, right? But like, if you want to perform an arithmetic operation, a conventional program is always going to get the right answer. And sure, there can be bugs in code, but For something like this, it's not likely to be the case because any programming language that implements arithmetic has probably been tried out by enough people that the bugs are moved out of it. So always going to be correct there. Machine learning systems can operate on much more complex problems, right? Like distinguishing a face from a grilled cheese sandwich. But at the same time, they're not going to be right all of the time. They're only going to be often correct, if you're lucky. So this, too, is something we'll come back to and sort of thinking about how to kind of design for and mitigate these kinds of things. Machine learning is also appropriate for, in a lot of cases, a different kind of problem than what conventional software is good for. So for example, when it comes to an ATM, there's probably not a lot of need for machine learning, at least in sort of the primary functions of an ATM, right? When you ask for a particular amount of money out of your account, there's really no interest in having that be sort of the amount of money that you asked for or something like that, right? It's like you want this to be operating in a true arithmetic way, and there's not much that kind of this intuitive understanding of the world would bring to all of this. So in terms of developing software, you can sort of think about it as conventional software being something where your relationship to it as the author is kind of as a dictator of sorts, right? You are setting out a very specific procedure and all of the conditions under which it's going to behave in different ways, right? And ultimately, you've mapped out in that code everything that the software could ever possibly do. Whereas with machine learning, you are operating much more in the role of being a teacher, right? Where its behaviors are ultimately sort of coming from the examples that you put in front of it, the experiences that you give it. So as kind of a very simple decision tree, when you're thinking about whether to use machine learning in some project or software that you're building, I think kind of the first question you should ask yourself is, can I articulate a concrete series of actions that would produce the desired functionality? If the answer is yes, you should definitely not use machine learning. There are some cases where stuff that you can do with conventional code, you could also do with machine learning. But probably any case that that's true, it would be more complicated and more error-prone to use machine learning. Believe it or not, with all the sophisticated stuff that machine learning can do, like for instance, beat the world's greatest Go and chess players, arithmetic is interestingly actually still a very, very difficult problem for learning systems. It's just sort of a different kind of competency. I can talk more about that if you want, but we won't go too much further. So yeah, anyway. OK, now let's start to talk about some of the sort of design opportunities. OK. So one of them is, of course, the ability to parse complex information in ways that were not really possible through conventional software. So being able to decipher things like facial expressions, also a wide range of inputs, right? So I think this is really exciting for a lot of different reasons, like being able to in this case, you have a learning system that's taking the input of a photograph and outputting some kind of high-level verbal description of it. Or here, you have what's called image segmentation, where you're passing in a photographic image, and the machine is returning back to you sort of a map of what each object in the image represents. Or being able to decipher things like the bones under your fingers. Or parse speech or anything like that. OK, sorry, I'll just say a few more words about this. So I think this is very interesting for a lot of different reasons. Certainly something that we think a lot about at Adobe because opening different ways for people to make things and articulate their ideas kind of in sort of the mode that is most relevant to them, I think is a really sort of powerful thing. In terms of everything from kind of people with physical disabilities being able to articulate things through other modes to just kind of the full range of kind of human intellectual diversity of people wanting to be able to kind of communicate things in the way that makes sense to them. I think that there's really tremendous opportunities in how machine learning allows us to transform how we communicate. Basically, that this enables us to have the machine come to us rather than us always having to go to it in terms of what the expectation and kind of the input mode is. And then, of course, we can learn a lot about user behavior and start to sort of understand patterns and proclivities in how people interact with software. I think when I first, first time I gave more or less this rendition of the talk, that conversation was probably a bit easier. Obviously, there are more and more kind of pitfalls to that we can see every day in terms of the implications of understanding user behavior. And I'll talk a little bit more about that in a minute. Okay, so another set of opportunities relate to creating dialogue. So this is a screenshot from one of my first loves in software. This is Maya, which is an incredibly powerful tool, but the number of features there is overwhelming, and this means that the number of menus and contextual menus and HUDs and everything else becomes completely overwhelming too. With sort of higher level semantics or higher level modes of input, we can start to think about communicating stuff, not through all of these menus, but instead, through other modes, and also through things like progressive disclosure, right? Of not necessarily kind of showing all functionality simultaneously, but instead having some sort of contextual understanding of what the user is up to, and then sort of, presenting the features that would appear to be relevant to a user at a particular time. So if you've ever played with one of these, and I will say I don't own one actually, like feature discovery is a definite problem, right? Like, the way that you sort of learn Alexa's features is by, I guess you can, well, I'll come to the other option in a second, but one is to just sort of try things out, right? And you're likely to find a lot of good stuff, but also you're likely to miss a lot of stuff. So there are definite limitations in this. Of course, most of them kind of try to take this kind of approach, right? Of like, if it's a purely voice interface, then you can say like, Alexa, what can you say to me, or something like that. And with Siri, it shows a list of things you can say. And of course, this is a big help, but I think still there are some limitations here. I mean, for one thing, ultimately, if your feature set were as large as Maya's, then it would sort of imply that then this list would be as long as the list of features in Maya, and then you're sort of back to the start with your problem, right? But again, with things like sort of contextual understanding, perhaps we can start to sort of narrow that down for any particular moment and have that be more contextually understood. Okay. Well, it's an underwhelming graphic for this, but designing building blocks. So, I'm not sure if this will always be the case, but I think in a certain way it's safe to say that it is, that the more that you can sort of design your interactions to be kind of granular and specific to sort of one directive or one piece of information, right? The better that you are likely to do in terms of the machine understanding what's being communicated, right? So, one of the sort of limiting factors of human language is that it has no kind of concrete bounds on it, right? Like, as per my winding sentences that you're listening to now, like, a sentence can have as many clauses potentially as you want. And sort of go off in many different directions and include sort of many ideas simultaneously. And machines today are certainly not fully up to the task of taking directions from very complex phrasing. And even though I think we can assume they will get better at that, there is perhaps some kind of limitation to that no matter what, and perhaps we can sort of look to the human mind as being an upper bound on that and say that, like, well, if something is greatly more confusing than a human can understand, then chances are it's going to take at least a very long time for machines to be able to make sense of it in the human domain anyway. Right, so the point here being that, like, as a designer, we want to think about sort of ways of helping the user to communicate ideas in ways that are then going to be understood by the machine, right? So, rather than just sort of giving a completely open-ended input, right? Sort of helping the user to put some guardrails around that and sort of, task them into one thing is going to help. We'll talk, I think, more about this in a second. Okay, so data, obviously, as per much of what's been said here, is of the greatest consequence to what you can do with machine learning. And the availability of data is a huge factor. And so, one thing that's really important in thinking about designing interactions with learning systems is how you can sort of start to fold information back in from the user. Sort of take what you've gathered from them, particularly things where you've been incorrect in interpretation, and try to use that as new learnings. So an example that I imagine you're all familiar with is reCAPTCHA, right? So this is, sort of a scheme in a sense to keep robots out of websites, but at the same time, that kind of human labor also helps to, at first, improve Google's ability to, to read, do OCR on books, right? Similarly, Google did this experiment called Quick Draw, where they asked people to draw objects of different types and do like sort of little quick doodles of them. And then from that, they built a tool that as you start drawing, it kind of suggests the rest of the shape. Often referred to in the press as being an autocomplete for drawing, which as an Adobe employee, I will say is not the direction that we're particularly enthusiastic about. But nonetheless, right, this, this sort of clever mechanism here is to get users to sort of participate in something that then sort of helps to improve functionality. OK, so I'll end this section with a quote from Buckminster Fuller. He says, "If you're in a shipwreck and all the boats are gone, a piano top buoyant enough to keep you afloat that comes along makes a fortuitous life preserver. But this is not to say that the best way to design a life preserver is in the form of a piano top. I think that we are clinging to a great many piano tops in accepting yesterday's fortuitous contrivings as constituting the only means for solving a given problem." I love this quote, and I think about it a lot. I think this is very important in thinking about kind of the paradigm shift that's happening in computing as a result of machine intelligence. There are, like, to speak about the sort of tools that I build for a second, like Photoshop in kind of its earliest incarnation comes as sort of a direct translation from the kinds of use cases and tools and skeuomorphic notions that that preceded it, in the world of the darkroom and in traditional graphic design. And so, many of the tools there are ones that borrow that vocabulary and iconography, right? You have things that look like pens and like scissors and scalpels and all that kind of stuff. And that's great from the point of view of being accessible, right? When a person sees a pen tool in a digital tool, they have some starting point in understanding what the relevance is and what you do with this thing, right? But at the same time, sometimes those analogies can be very limiting because it paints for the user the idea that this is all it's good for, right? And so I think it takes a certain amount of time for people playing with Photoshop to start to kind of see beyond those things, right? And to start to say like, well, yeah, like this is, got the sort of the vocabulary of conventional tools, but we can do something with it that is completely outside of what was possible in the world of the darkroom. And so I think, while there are lots of reasons why we do sometimes want to go with that, I think, we also have to be sort of true to the nature of what the technology suggests and kind of try to put, its own kind of unique properties forward. And so in the last section of this talk, I'll show some ideas about kind of how we're thinking about that in terms of building like, machine learning based creative tools and how we sort of have to try to move away from some of these analogies. Okay, design challenges. Mitigating the risks of erroneous behavior. Okay, so these are, sort of simplistic, but hopefully they're a bit helpful in kind of thinking about how you deal with some of the things that, are potentially challenging about the ways that machine learning is different from conventional software. So first of all, like when you're presenting behaviors to the user based on your understanding of them, it's often useful to restate the interpretation back to them, right? It's like, for instance, if you think that they've said that they want to delete something, perhaps you want to make sure that that's in fact what they were getting at before you actually go ahead and delete it. And provide fallbacks. So, while intelligent functionality can be really powerful, if it's not doing what you want, often it would make sense to include some escape routes so that people can, sort of try to, to operate in a different way. Of course, this is not always going to be easy, right? Because if the thing that they're trying to do requires the intelligence of this feature and that feature is, not working well, then it's probably the case that you couldn't have used a conventional feature in the first place. But to some extent, there are ways of kind of getting around that. So perform rigorous testing. And so I think kind of, back to the earlier part of the conversation, one of the things that's, I think, really, really important here is to try to test outside of the pool of, the experiences that the system was originally developed within, right? So, if you've got 5 people in one office working on some particular feature and they're kind of feeding their own inputs into it, right, then it would make sense to try to test it with other people in different environments. Because those conditions are going to be in many ways kind of ingrained into kind of the understanding of the machine. And you want to make sure that you've also sort of observed the red car, so to speak. That the experiences that differ greatly from the place where you did it. And I think there's a quote that's often ascribed to Marshall McLuhan, although apparently he didn't say it. I don't know who discovered water, but it certainly wasn't a fish, right? And that's very much true of all of us in the sense that it's very kind of hard to notice all of the sort of things that you take for granted about your own environment. And so really, as much as it would be nice for us to be able to see outside of ourselves, there's a lot of ways in which we can't. And so ultimately we have to try to impose that on ourselves by sort of setting up mechanisms that sort of force us to see outside of ourselves. This is not always applicable, but there are, for many kinds of learning systems, performance metrics. So, with something like image classification, where you're trying to identify what object is in an image, often you don't just get back the, person or something, but instead that is basically sort of communicated in the form of a number, of basically sort of, all of your categories are laid out, and, person might be sort of the highest numeric output, giving back usually not a pure 1.0, but like a 0.9% chance that this is a person and maybe a 0.002% chance that this is an apple. And so sort of looking at that in terms of how you design functionality is also important, right? And so sort of kind of a judgment call, right? But do you want to serve back to the user a perception that only got a sort of 20% confidence if that was your highest score? Or should you instead say to the user, not really sure what this was, we got to do this again or something? And then as much as I, and I imagine you are interested in sort of putting out the latest and greatest and sort of getting that out into the wild, also I think have to sort of be a little bit prudent in resisting features that are not yet ready for prime time. And of course, particularly where systems involve people's lives and serious consequences, important to make users aware of those risks, right? So some things can fail cheaply, right? If I don't know, if in a design tool we thought you were trying to do one thing and you were actually trying to do something else, probably not a huge consequence to us taking a stab at it, and you could always undo it, right? But if we're talking about a self-driving car, then it's much more serious to think about being wrong. Masking faulty assumptions. So okay, this is getting to be an old story, but a couple of years ago, Target, the retailer, was doing this thing where they were, I think as many retailers are now, sort of trying to make sense of what you buy and what that says about you, and try to infer some things about who you are as a user. they're all doing it, of course, but sort of how you surface that back to the user is of great consequence. So in the case of Target, they sent to one particular customer some kind of flyer that basically said, like, congratulations, like, on your baby. And this was this particular person was a very young woman, and her parents intercepted it and were very surprised to hear all of this, and sort of flipped out at Target about it, and then ultimately found out that the kid was in fact pregnant, and didn't hold it against Target. But nonetheless, like what you sort of put out is something that it's very much a design decision, right? And so perhaps rather than sort of stating the perception of the person, which can often sort of feel very uncomfortable, instead you can sort of suggest what products they might be interested in, and maybe they're interested in them and maybe they're not. But trying to typify the person themselves is much more of a risky business. Okay, creating sanity checks. Okay. So this was a Microsoft project called Tay. It went very, very poorly. Although I heard someone from Microsoft speak about it, and because everyone was kind of baffled by what happened. So let me first explain what happened in the States, and then I'll say what the Microsoft researcher said. But basically, it was this chatbot that was on Twitter, and it would learn from user input. And so within a couple days of going live in the US, people had taught it like all sorts of hate speech, and it was saying really terrible stuff. And so the reaction was kind of like, how did Microsoft screw this up? Like, why didn't they put any safeguards in? Which I'll speak about those safeguards in a second. I wondered this myself. And then I heard one of the project leads from Microsoft speak about it, and what she said was that they had launched it in China, and that none of this had happened at all, that it had gone perfectly smoothly. So clearly, that says something about the state of US discourse. But yeah. So anyway, in terms of safeguards, like one of the sort of surprising things about this was that while natural language is very complex and it can be really difficult to sort of figure out whether something is sort of like subversively or subtly a nasty or kind of digressive thing to say. Like just there's certain words that you could just filter without any machine learning of just doing kind of dictionary lookups and know that this counts as hate speech or whatever. And they weren't doing any of that, right? It was like people were teaching this correctly spelled words that I think anyone would put in that kind of dictionary, and they hadn't put that kind of pass on it. And so the point being that that even if like sort of the nuanced kinds of stuff may be kind of difficult to weed out, there are sort of safeguards that you can impose, at least on the really obvious stuff. Okay, so the next part I was going to talk a little bit about Adobe-related stuff. But before I do that, any sort of questions or anything? I think as I was saying, like I think a big sort of motivating factor for bringing machine learning into software is being able to understand a world that does not lend itself to sort of really neat, tidy rule systems. I think in general that's kind of the big thing, and of course the human world and the natural world are very complex and often kind of defy sort of really neat rule systems, and so I think in a very general sense that's kind of why. But does that answer your question? So interestingly, and this is actually not that often stated about him, but Alan Turing not only invented sort of the original paradigm in computing, but wrote a paper that quite well speculated on what neural networks would and should be. He called them unorganized machines, and by comparison, conventional computers, which he also, of course, theorized, he called organized machines. And basically, he sort of did a really good job of outlining sort of how you would perform inductive behaviors in a learning system. So it's been there. It's been there since the 40s. I think kind of the main reason is more of a Moore's law thing than anything. So performance, like what he was kind of working out on paper was how like an individual, like the model of a single neuron or of like two neurons would work, and that can solve a certain type of problem. But complex problems like the ones that people are tackling with machine learning now involve usually on the order of many millions of neurons, right? Like a sort of contemporary image recognizer or something to that effect is usually going to have like something like 100 million neural connections, and so like the performance of that, like by contemporary hardware standards, like to run a system like that. I mean, I'm just sort of ballparking it just for the sake of whatever, but. To do something like that well, you should probably spend like about $3,000 on hardware, in like by contemporary standards, right? So basically, like if you assembled all of the world's supercomputers in like by the end of World War II, or let's even give it a decade later than that, all of the world's computers together would be less powerful than that, So essentially. This is at the core of it. I think the other thing is it's hard to picture, like what 1 or 2 neurons can do versus what 100 million can do, right? Is like the scale of that I think is very hard to picture, right? So when you see that kind of worked out with 1 neuron, I think it's very difficult for a person to imagine sort of what the possibilities are for the use cases. And so it's not until the hardware sort of starts to come in, into maturity that you can begin to tackle that. Okay, so Adobe. Yeah, so I think when people think about AI and creativity, there are lots of understandable concerns about like is this going to replace designers' jobs? Is this going to make it so that designers are not really doing creative work? They're just kind of managing machines doing it for them. Our perspective, my team's perspective, is something different from this, which is that in a lot of ways, machine intelligence can actually do something very positive for human designers, which is enable us to do more and to think bigger. And I think actually this gets to sort of the point about kind of the being able to picture complex systems. So in kind of a different area of design from Adobe's products. In, say, the world of CAD and architectural design, when CAD tools came around, it's not like architects were no longer needed, right? The Florence Cathedral took about 140 years from the original conception of the project to the final completion of the building, whereas the far, far more complex Burj Khalifa took only 5 years from conception to completion. There's a bunch of things that changed about the world, one of them being construction materials and processes. But certainly one of the big changes here is CAD software, right? The ability to picture such a complex system and develop it is really, this building is just far too complex for any one person to really kind of store mentally, right? And so the software sort of provides a way of structuring all of that complexity and not having to keep it all simultaneously, but to be able to sort of move through the parts and look back to the whole and back and forth and so forth, right? And so CAD software doesn't replace architects. It allows architects to do more and to think about much more complex systems. In a different area of domain, a different area of design, I think, sort of going back to what I was saying about sort of, sort of the skeuomorphism of tools like Photoshop, while Photoshop kind of comes from existing needs and existing use cases and kind of analogies, at the same time, its users went beyond that, right? And sort of saw opportunities in what could be made through those tools that's really far too complex for anyone to have sort of thought about from the perspective of a darkroom and like doing dodging and burning and that kind of stuff, right? And so it's only kind of through these tools that creatives are able to sort of take on these increasingly complex ideas. The tool is ultimately sort of helping you to structure the complexity of your own ideas, right? And to scaffold your thinking in a lot of ways. And so I think in addition to this being of relevance to professional designers, I think machine intelligence also kind of transforms the story of making creative tools accessible to everyone. And so, one of the things that I've been kind of pushing on in our work is like that, like user research kind of, has historically kind of bucketed users into, a variety of categories, right? And so we have ones like hobbyist and novice and aspiring creative or aspiring professional and creative professional, right? And I think that in a certain way, it's sometimes kind of taken as Pollyannish to say like, well, maybe this tool could just be for everyone, right? But I think actually that's starting to be true to a certain extent. That a tool that you can communicate ideas to in a way that is sort of more organic to your thinking, perhaps actually can be for everyone, right? If you are a novice and your tools, your ideas in a particular domain of design are not that sophisticated, then the tool can work with that. And if your ideas are more sophisticated and you see more depth in this particular area of design, then perhaps that we can sort of come to that as well. And so I think that this is kind of changing how we should look at user research and how we think about sort of product development. Because conventionally learning a tool like Photoshop is about learning how to map your ideas from sort of the form that they might have in your thinking about the content into sort of some kind of sequence of command. But if instead you can leave them there, right, and communicate those ideas like in kind of the language of the content, then learning the tool is a very different thing. So I want to show kind of some of the powers of machine intelligence, some of the stuff that's happening, particularly in these examples in the world of imaging. So this person does not exist. Maybe you've seen the website thispersondoesnotexist.com. So this is produced by a GAN, and GAN stands for Generative Adversarial Network. And basically what it is you have sort of two component learning systems. One is a forger and one is a forgery detector. And the forgery detector is trying to make a sort of binary prediction. Either the image that it's looking at, it's going to predict that it's a forgery, or it's going to predict that it's an image that came from the real data set, right? And you're intermittently showing it examples that are either coming from the forger or from the data set. And essentially what it's having to learn in order to make those kinds of predictions is what kind of patterns are likely to occur within the data set that it's observing, right? And so then correspondingly, the forger, as the forgery detector gets better, the forger has to sort of learn how to understand those patterns and produce them, right? It has to kind of create increasingly good representations of the kind of things that are likely to occur within the data set. And so these two systems ultimately elevate one another until you can synthetically produce people that are more or less indistinguishable from real. OK, so this is using the same basic technology. There's some architectural differences. But this video of a zebra is actually a video of a horse. And so the way that this works essentially sort of conceptually is that if you are able to sort of learn the patterns of what like horseness is and what zebraness is, then you can also kind of learn to understand what the absence of that pattern is, and then elevate that pattern, right? And so in this video of a horse, we can kind of elevate the qualities that we understand to be the patterns that should be observed in a zebra, and therefore kind of bring them out in a horse. I wish I'd included it, but there's this great example that someone ran like a picture of Vladimir Putin on a horse, and like he and the horse are both transformed into looking like a zebra. So of course, this sort of goes too far, if you want it to. OK, and so these birds were generated from this text description. Also using the same sort of basic technology, but instead sort of adding one or two architectural differences so that you can kind of try to learn relationships between descriptions and what the sort of visual patterns should be. And the list goes on. So like these are sort of transformational tasks. Like And this one I think is interesting in sort of an algebraic form, right? A man with glasses minus a man without glasses plus a woman without glasses gives you woman with glasses, right? So there's ways of sort of articulating ideas in that way. And, you know, well, I'll come to some of these later, but this is age advancement, being able to change the age of a person, being able to change the season. This is not just like an issue of color correction here. It's actually sort of going in and, you know, in the case of winter, say, understanding that you know, that there is a pattern that associated with winter that is ultimately going to put sort of these white speckles on things. And so it's kind of going in there in a very granular way and adding that. OK, so what can Adobe, or whatever, I don't want to make this an advertisement, but you know, what can we do with these kinds of things in design tools? So you know, naturally we can improve things under the hood, right? So something like content-aware fill. The sort of traditional form of content-aware fill in our tools ultimately does sort of pattern extension. So it kind of looks at the pattern surrounding the region that you're trying to fill, and it figures out how to sort of smoothly fill that in. So if, for example, you've got like a, you know, whatever, like a soccer ball sitting on grass, you want to, you know, remove the soccer ball. Essentially, it's going to sort of figure out how to propagate the texture of the grass onto it. That's great if you want to do that, but what if you are trying to sort of fill an area where, say, like if you've got sort of just the mouth region of a face missing, right, and you want to fill that out? Well, you know, this is not going to work with sort of the pattern extension because, of course, if you extend like the pattern of the cheeks, you're just going to have sort of the absence of a mouth filled with more cheeks, right? And that's of course, because this is sort of a dumb understanding of the content, right? If instead we could learn how to do this with an understanding of the content, right, where we basically sort of train on many examples of images where we take an image, we sort of randomly remove a portion of it, right, and then we sort of train on the relationship between those, then ultimately the machine is going to sort of learn kind of what patterns are likely to occur there, right? And so in looking at many examples of faces, it would learn, you know, the kind of pattern that should make up the mouth, and therefore we can fill that in. OK, so I use this as an example of stuff where we can kind of change the functionality without changing anything about the interaction patterns, right? This is something that we can and are doing, you know, under the hood, and you know, the functionality will improve, and the user doesn't have to learn a new workflow or anything like that. Then there's other places where we can at least kind of stay somewhat in the vocabulary that users are acclimated to, but you know, like introduce some better functionality, but that also suggests some changes. So this is what's called neural style transfer. And you can think about it as being at least sort of somewhat similar to you know, a conventional image filter, right? But rather than an image filter, which is, you know, sort of just like a procedure in code, this instead you know, takes a user's image and a reference image, like say, you know, the work by Van Gogh or a famous artist or yourself, and sort of figures out what kind of the stylistic properties are in the pixels of the reference image, and then sort of figures out how to apply that sort of characteristic to the user's image, right? So in a lot of ways, very similar to, you know, to a conventional filter, but it does suggest some transformations in the user experience because, you know, we now have sort of the need for a reference image, right? So it's sort of coming a little bit more into kind of some transformations of what the software would actually look like and how you actually interact with it. Going much further, you know, we can also, I think our real goal is to think about how to provide creatives with new ways to express and explore their ideas. How do we sort of go beyond the existing paradigms and really sort of take full advantage of what's possible now? So that's the area I'd most like to talk about, and a lot of it is kind of a stay tuned sort of a thing. In terms of what we've released so far, a lot of it kind of falls into these first categories of things that we can do without kind of radical transformations. So you know, here's image colorization in the latest rendition of Photoshop Elements. Right? Given a black and white photograph, we can sort of predict what the color output should be. There's an automated rendition of this. Right? But if you think about it, like, this also does suggest some places where you might want to sort of create new mechanisms of input from the user. Right? Like, there's certain types of objects that probably, your sort of statistical understanding of what is likely to be the case are going to be right. Like, there's a good chance that this is grass, and there's a good chance that grass should be green, right? But other things are kind of harder to know, just sort of in the abstract, right? Like, so, what color is this dress actually, right? The luminance alone does not fully suggest that. So, what kind of mechanisms could we introduce so that the user can then sort of put indications into this so that you can actually control those kinds of changes? One being, sort of putting color swatches on here and sort of say like, just like put a little dot of color there, and then that sort of tells the system, what direction to colorize it. This too, in sort of a more automated domain, being able to do things like reduce grain and noise, and all sorts of artifacts of that kind. This is sort of responsive design for video, effectively. So basically sort of doing pan and scan, but sort of figuring out the sort of crop of a particular video sequence based on the device form factor that you're ultimately targeting. Right? And so obviously there's kind of a naive, non-intelligent way of doing this of just like, whatever, crop to the middle, right? But this works with content understanding. So, for instance, you can see here, even though this face is actually not the center of the image, right? It has adjusted on that. So it's sort of, prioritizing sort of what, would generally be considered like the important content of human faces. And then we're doing lots of stuff in Experience Cloud. And just for my own curiosity, like how many people are aware of Experience Cloud? Yeah, interesting, interesting. My neighbor's in advertising, and when I told him I worked for Adobe, he was like, "Oh, Experience Cloud." He's like, "Okay, so that's who knows." Yeah, but it's like, okay. So I want to talk sort of about designing for emerging technologies. I talked a little bit about this, and so the main point I wanted to raise here is to say that sometimes new technologies do fit into existing UI UX models. And when they do, it's a relatively straightforward thing to bring them into the software. And in terms of sort of software development processes, this is like sort of the way that things have often worked at Adobe and elsewhere is what's referred to as tech transfer, right? Where new functionality would be sort of developed more or less in full within the research division. Right, like they might say like, okay, we've kind of realized that there's a new algorithmic approach that we could take to some particular problem, and we can kind of build this up fully, and then hand that, or basically sort of advertise that to product teams that might be interested. And if a product team like Photoshop picks that up, then the design organization will get involved, and they'll just sort of figure out what the UI should look like for it, and the whole thing is done, right? But the important point being that sort of like the story has kind of ended with research, and everything else is kind of a foregone conclusion in that kind of process. But there's other places where this is not going to work so well. And I think that's kind of what we're facing now. And it's really suggesting a very new role for design. So this is a demo called GoGAN, developed by NVIDIA. And what this allows you to do is you draw into this sort of very crude kind of Mac Paint style interface. And oops, sorry, I had whatever. Like you sort of are drawing the categories of things, right? So you choose one of these object types from the palette, and then ultimately sort of draw what the shape and the placement of that object should be. And then the learning system sort of translates this into kind of a photoreal representation. This is a research demo, right? And it feels like one, right? This is not necessarily kind of the right way that, for a person to draw images with this kind of technology. Having played with this thing a lot, I can tell you that, drawing mountains and stuff in this form, it's relatively straightforward. But when you want to like draw a horse in silhouette in this sort of very crude brush, it goes very poorly. I'm not a terrible drawer, but we've tried it even with like expert painters, and it's not necessarily the best way to communicate ideas. And so if research were to sort of put this kind of technology forward and say like, we're done, now just put this in, right? This is not something that that we can treat that way, really, right? Like design has to have a much earlier involvement, and ultimately, sort of affect how the technological development is going in terms of what the interaction pattern should be. And so this suggests a much closer relationship between the research, the product, and the design. And so I think that transformation is occurring across a lot of companies, and particularly ones in this kind of space, where ultimately, essentially, we have like a major paradigm shift going here. And when this paradigm is mature, in 15 years perhaps, it will be possible to put out like learning-based features into software without kind of having to raise all of these questions. But in the time period that we're in now, these things are all very new. And so all of the things that we sort of looked at earlier in this, all are things that have to be sort of factored into the technological development right from the start. Yeah, fair question. So, I mean, like, it certainly could be in the other way. The reason I drew it this way was just because the conventional tech transfer is that a product team has to say, yes, we're interested for anything to move forward out of research. In fact, in the processes that we're doing now, it's actually kind of like, I would say that the right way to diagram this would sort of be to say like a loop between design and research with sort of sometimes like checking in with product, and then more kind of work between design and research, and then ultimately the final stage being putting it into product. That would be a hard diagram to draw though. But, so one of the ways we sort of look at these technologies is like, well, what are bleeding edge users doing? So if you search on Twitter or Instagram for the hashtag GoGAN, you'll find countless examples of people making stuff with this very crude tool, and it takes a lot of work to to really actually sort of put things through that pipeline. But nonetheless, people are doing it, and it's very, very interesting to see kind of the painting techniques that are emerging within this in terms of how people sort of think to create this image. Right? Like, for example, so this put clouds in the skies. But the interesting thing is that the data set, clouds never look like this in the data set, right? So the fact that that works is almost like a hack that has been sort of discovered by a lot of people performing a lot of trial and error. And so, it's very sort of interesting to see what people do with it. I think this is sort of another important thing in that kind of loop of research and design and product, is that I think sort of the best thing, sort of the opposite side of what I was saying before, of like that you want to make sure you test with users, like so that you don't screw up and like kind of make sure that you are not supporting something that they were trying before. Sort of from a different perspective, I think kind of your best hope can be that that people will go beyond what you did, right? Like if people never sort of envision a use case for what you've built beyond what you imagined, then probably your product is really not thinking big enough, right? Like I think what you really want is people to take it much further than anything you really thought for it. People are doing goofy stuff with this, like using grass to make the nose of a dog. And perhaps the most interesting one is this, which is people doing sort of a form of what's sometimes referred to as photo bashing, right? Which is something that people did with like conventional photos of like, you take some stock image and you kind of pull the grass out of it, maybe do some clone stamping with it and like, mess with it and integrate it into a larger image. And ultimately you can make sort of this much larger scene. And in some ways people are using this technology to do that. And despite the resolution limitations, right? So this particular research model only outputs a 512 by 512 image. So in some ways, bless you, you could see that as being something that is sort of not fully ready for professional products. But when you look at people doing stuff like this with it, right? God, this is kind of dark here. But in any case, it's a really cool kind of matte painting type thing. And ultimately, this is part of that image. And they've sort of painted around it, right? And so sort of seeing how people start to use these things is, of course, really important to thinking about what we should be doing with these kinds of technologies in our products. OK, so the last thing I want to talk about, the cutting edge is serrated. This is from a talk that I gave to the research division. And I think kind of like the way that I think about what a role of design for emerging technologies is that new technologies are often very uneven. And I think that's particularly true of machine learning. So an example that I think of is like when IBM Watson won at Jeopardy, it completely trounced the human champions. It won by a very large margin. Nonetheless, when answering a question that related to a US city, it said Toronto, right? And so everyone was like, what? Like, it's like such an obvious, sort of gap that it should have just known. And so, the thing is that these technologies are gaining their knowledge of the world through these examples. And apparently that one didn't kind of have coverage on a few particular things. And so even though statistically it was way better than, than any of us are at Jeopardy or Go or chess or anything like this, like there are ways in which there's a real unevenness in that. And of course, from a user point of view, that's very hard to understand and also can be very disappointing. And so the technology alone, I think, particularly when it's really on kind of the bleeding edge, is ultimately something that design is needed in order to kind of even out that surface, right? To sort of fill the gaps in where those expectations would have the user think that, that things are going to be more than they actually are. And to sort of make everything about it cohesive and to communicate what the limitations are and ultimately kind of make the straight edge out of the serrated one. Thanks.